Section 3 here then is on Charles's law. Charles's law is about temperature and volume. And so here it says that they are directly related. That is, as one goes up, the other goes up. So if temperature goes up, volume goes up. And if temperature goes down, then the volume goes down as well. The two go in the same direction. And again, this is under constant pressure and amount. Once again, they have a cylinder to illustrate, and I personally think of this as well, of a cylinder like this. But if we heat the gas in here up, then the gas is bouncing around more rapidly, and as it's bouncing around more rapidly, that would increase the pressure. But rather than the pressure increasing, because this has the ability to move, instead it just expands. And so then you can see expand out. This is why you don't put aerosol containers into a fire, because they can explode. I actually have a student who ended up with shrapnel in his face because he tossed a aerosol can into a campfire and it blew up on him. If we instead cool this, then when it cools, then the particles are bouncing around less, and that would then cause the volume to contract there. It's going to shrink. This is why your car tires will go flat when the weather turns cold, and you frequently have to repressurize them because of that, because the gas particles are no longer bouncing around as much. Mathematically then, because they're directly related, the formula ends up like this, and so that is our new formula. Again, it comes up in the combined gas law, but here on the next slide, they just show the different ways to rearrange it. I don't think that's necessary. And then here they ask us to do one of those rearrangements. Personally, I don't like doing my math like this. I would much rather plug in numbers, be given a question, and be given 3 of these, and then be asked to solve for the other one and put in numbers and then do the math with the numbers rather than with the letters. But math with letters does work here. And so if we want to rearrange this one to solve for T2, there's 2 ways to handle this algebraically. One way is to multiply both sides by T2. T2 is going to cancel out over here, and so then we end up with T2 times V1 over T1 is equal to V2. Then we can divide both sides by V1 and multiply them both by T1, or we can divide them both by V1 over T1, which is then the same thing as multiplying by the inverse of that, V2 times T1 over V1. Your textbook likes to list it out as just the volumes over one another and then have the temperature separate, and that works. They're the same thing mathematically. Having said that, there is a much simpler way to do this, and that is to do a process known as cross multiply and divide. So we multiply the things on the diagonal. It's just a shortcut for doing the math work that I was doing down here, but you end up with V1 times T2 is equal to V2 times T1. You'll notice we have pairs on each side, that we have a 1 and a 2 on each side, and then we want to get T2 alone, so we divide both sides by V1, and then that cancels out over here, and we're left with the same answer. T2 is equal to V2 over V1 times T1. Either method gets you there. Go with what you're comfortable with mathematically, although I'll say most students do cross multiply and divide, and it's how you'll see me working them out as we get into practice problems like this one. We're given here a volume initially, a temperature initially, and if the temperature drops to this, so there's a temperature final, then what's the new volume final? Well, one thing is we always have to use Kelvin for our temperatures. So 21 plus 273 gives us 294 Kelvin for T initial. And the next one's easy. 0 plus 273 is just 273 Kelvin for T final. And now volume initial over temperature initial is equal to volume final over temperature final. Now we plug numbers into this one, and we have 785 milliliters over the initial temperature of 294 K is equal to a volume final that we're solving for over 273 Kelvin. At this point, we cross multiply and divide, and we end up with volume final times 294 Kelvin is equal to 785 milliliters times 273 Kelvin. Divide both sides by 294 Kelvin, and the Kelvin units are going to cancel out. We're left with milliliters, which makes sense for a volume, and we end up with V2 is equal to 729 milliliters. I didn't do a check at the beginning, but we have our temperature going down, and if our temperature goes down, then we expect the volume to go down, and sure enough, it did. So that sounds like a good answer there. Sig fig side note, personally, when I'm given temperatures in Celsius and I convert them to Kelvin, I tend to count the Kelvin temperatures as my sig fig units. And so everything here then has 3, so my final volume should have 3 as well. I will point out that as we keep going here, I'm going to drop doing the kind of middle steps on the algebra. At that point, it's just algebra, and you should be familiar with that. Certainly, I would encourage you to take your time, work it out, make sure you follow it. If you're stuck, don't hesitate to ask me questions. I'll gladly help you with those aspects, but I'm kind of going to jump forward to just volume final equals something instead of showing the work in between. I'll also add in here, rerun this problem real quick using the Celsius temperatures for this one, and you'll see real quick why it doesn't work. You're going to get an error when you go to punch temperature final in here and try to divide by 0. You can't divide by 0. Not only that, but if you're given a negative temperature, you'll end up with a negative volume, and negative volumes just aren't possible. We can have something take up space or no space if it's not if it's not a gas, if it's not a matter, but something like light or energy. But try to imagine something that takes up less than no space. That in fact, when it takes up less than no space, it somehow creates extra space. It just makes no sense. Temperatures have to be on a non-negative scale, a scale that starts at 0. Another practice problem here. We have a volume initial of that, a temperature initial of that, and we're going to add the 273 to get that into Kelvin, which comes out to be 291 Kelvin, and we're asked to solve for the new temperature, the temperature after in Celsius, when the volume after is that. So volume initial over temperature initial is equal to volume after over temperature after. Plugging in the numbers, we end up with 420 milliliters there, 291 Kelvin there is equal to 640 milliliters here over temperature after here. Rearrange that, and we end up with temperature after is equal to 640 milliliters times 291 Kelvin divided by 420 milliliters. Milliliters cancel out, and we are left with 443 Kelvin, which makes sense for a temperature. We were asked to solve for it in Celsius, though, so then we have to minus 273 Kelvin, and we end up with 170 degrees Celsius, which is choice B up here. I'll also point out that the volume went up, and if the volume went up, then we'd expect the temperature to go up. So this one here was flat out not possible. You'll notice here that one of the wrong choices is the correct answer in Kelvin, and so they've just changed the units on you. Be careful with your units. One final check here as we finish. This one is combining the two gas laws, or bringing both of them together here. So this one's talking about pressure and volume. So this is Boyle's law here, but that's not what they're asking. They're saying that when the volume decreases at a constant temperature and amount, then the pressure is going to increase. When the temperature decreases, the volume is going to also decrease when pressure and amount are constant. That one is a Charles's law. Here we have another Boyle's law, and we're told that the volume goes from this to that. So the volume is increasing, which means the pressure must be decreasing, again at constant temperature in moles. This one here then is another Charles's one, because we got volume and temperature at a constant pressure in mole, and here the temperature went up. And so if the temperature goes up, then we expect the volume to go up as well. Their answer key has the words increases and decreases as it's supposed to. I assume that you can follow along that I did up and down arrows for increases and decreases. And that finishes section 3.